and gentlemen, so today we are very happy to invite Professor Akira Ono from Tohoku University. So he will give a seminar title is Cluster Production in Expanding Nuclear Matter in Intermediate Energy Heavy Ion Collision. Ono-san is very famous in the nuclear reaction theory, especially for the transport model development and applications. And Ono-san finished his PhD in science at Kyoto University in 1995. After working at RIKEN as a postdoc fellow for about 1 year, he got a permanent position at Tohoku University in 1996. I think in that time, Ono-san worked a lot of collaborate with like Horowitz-san for AMD development. And his main research interest has been the many body dynamics in nuclear actions and the properties of the nuclear matter realized during the reactions. Recently, he is participating in several international collaborations. I think most of us know some projects like transport compilation, since in this nuclear reaction market, there are a lot of transport model like BUU, KMD, and various versions. So they did a lot of interesting and excellent work for transmodel compilation and evaluation. So today, it's our great pleasure to invite him give a talk on cluster production. Actually, cluster production recently is also very interesting in relativistic heavy ion collision, like deuteron, proton, even its fluctuation. So in this intermediate energy heavy ion collision, cluster production is also very interesting topic. So please, Professor Ono, give your talk.
Thank you very much for very kind introduction and also for giving this opportunity to talk to all of you on our recent works on cluster production in heavy ion collisions. At the beginning, I will give some general introduction on clusters and equation of state in intermediate energy heavy ion collisions. And then I will talk about our approach, which is antisymmetrized molecular dynamics model. And I include cluster correlations in this model. And then I will show that cluster correlation or product production is really have a very strong impact on the collision dynamics. And so we have to simultaneously understand the clusters and the collision dynamics. I will show some examples. And then at the end, I will briefly talk about whether we can get some information of the symmetry energy of the nuclear equation of state from the cluster observables. Okay. And I am in this talk, I am mainly interested in this kind of heavy ion central collisions, and around this energy mainly 300 MeV per nucleon. And then this is a result of a calculation, but probably it's true that at some stage the two nuclei overlap and some compressed system is created, and we can reach twice the nuclear saturation density rho 0. And then system is rather quickly expanding, and at the end we will see many. Okay, there nucleons are emitted, but also there are many light clusters like deuteron, triton, helium-3, and helium-4. And also there are heavier nuclei. And so this kind of thing that I want to talk about in this seminar. And one of the main interests is maybe this high density stage. And of course, if we are only studying a single nucleus, we cannot reach such a high density. So heavy collision is very important to achieve high density. And by this, as a property of nuclear matter, we can reach somewhat high density. Okay, this figure is covers a very wide range, but from this reaction, we can reach twice the nuclear matter densities around here. And also, we need to know that the system is rather highly excited. So temperature is not zero, but finite temperature, even if the system is thermally equilibrated. But it's a question whether such a thermal equilibrium is reached in this kind of reaction. But anyway, this heavy ion reaction is almost a unique way to go to high density. And one important thing is that we can change the number of neutrons and protons of the reaction. And in the theoretical calculation, of course, it's easy to put different numbers here, but experimentally, a lot of efforts have been made. So we can now, by using the radioactive isotope beam facilities, we can go to somewhat neutron-rich system, and we can somehow vary the neutron-proton asymmetry. Okay, and equation of state of nuclear matter may be written as a function of the proton density and the neutron density, or we can equally write as a function of the total nucleon density and the difference between neutron and the proton, normalized by the total density. And then for the symmetric system, symmetric means that the proton and the neutron densities are identical. Then we have this kind of equation of state, and there is a saturation point around here. But if we change the neutron-proton asymmetry, and for pure neutron matter, the equation of state may be like this way. And so if this is expanded as a function of delta, this second order term is called the symmetry energy. And the equation of state of nuclear matter is closely related to the neutron stars, the structure of neutron stars. And here you may frequently see this figure that shows a relation between the mass of a neutron star and radius of the neutron star. And once the nuclear equation of state is given, then all neutron stars should be on one of these curves for given equation of state. Okay, but the curve depends on the equation of state, so it's very important to know the equation of state. And from the astronomical observations, we have some, currently we have some constraints such as the existence of twice the solar mass neutron stars or gravitational wave observations. And so this is from the Paris, it's an observation by nice collaboration. So we have some constraints, but we still have large error bars or uncertainties. And from the nuclear physics side, here I mainly talk about traditional nuclear experiments at relatively low energies, such as in RCNP or RIKEN. And we have some constraints. We can draw some constraints on this mass and radius correlation curve. This was made by Sotanism. But here we at high, for very heavy new stars may be at the center of the neutron stars, and maybe quarks or hyperons may appear in some phase. So these things we cannot reach by intermediate energy reactions, but then we can get still some information around here. Okay, and focusing on this kind of collision, as I already said, we can reach high density here, and this shows the time evolution of the neutron density. Neutron density is shown by red, and proton density is shown by blue as functions of time, this axis. And we can, so if you add these two, we can reach twice the saturation density at this stage. And okay, so this is this neutron-rich system, relatively neutron-rich system. So we have higher neutron densities than proton density. And if we take somehow the ratio of these two, so then we have this line as a function of time. So this means that, okay, this dashed dotted line shows the neutron-proton ratio of this total system. We already have a neutron-rich system. This is much larger than 1. So but the central region, so this is some result of calculation, but it shows that the central region of the system becomes less neutron-rich. Okay, and this is because at high density we have a repulsive symmetry energy like this. So we don't want to be neutron-rich in the high density place. So high density part becomes less neutron-rich, and this amount of the change depends on how the symmetry energy is, like this soft one or like this stiffer one. So if you want to really, if we can really observe this effect, we can get rather strong information on the high density symmetry energy. But of course, the question is how we can observe this effect. And this has been proposed that the pion ratio, pi minus, pi plus ratio should be a good observable, because the pions are originating from high density phase, and this, so pi minus and pi plus have different isospin, and this should be related to the neutron-proton ratio squared. So because of how, if you think how these are created, we can roughly estimate that it should be related to this. And then, so people have been interested in this observable. But in this talk, I'm not go much into this pion observables, but I will mainly talk about the nucleon observables and cluster observables. And okay. But important thing or something we need to worry about is that this is a situation at the very early phase of the reaction, and this is how experimentally observed. So between these two, we have to consider that time evolution of the system, and this part strongly relies on transport models. So we need to have some model to calculate the time evolution from here to here, okay? And okay, another thing is that the clusters are really important. And generally, after collision, many clusters and fragments are formed. And this figure shows that how the total protons in the system are bound in clusters. For example, so this is a similar, this is a typical case, and maybe I think there are about 100 protons in the system. And this shows that only about a quarter of the total protons are emitted as free protons, and other 75% of protons are bound in clusters, deuterons, tritons, helium-3 alpha, and also maybe 10 or 20% of protons are bound in heavier nuclei like lithium and so on. Okay, so actually a proton is a minor part of the total system, and to understand what's happening in reaction, we need to know, we need to describe how these clusters are formed. And this is really a challenge to theorists and transport models, but because the description of clusters is not very easy. And this shows an experimental data, and low energy part were taken from the indoor data taken in Ganil, and higher energy part was taken from the data of FOPI collaborations taken in GSI in Germany. Okay. And also clusters are very important not only in heavy ion collisions, but also in the study of nuclear structure. And if the nucleus is somewhat excited, like near the threshold of particle decay, typically cluster structure appears around here, such as a molecular structure or something like gas or condensate of alpha clusters. Okay, so this is very intensively discussed in the field of nuclear structure. And then in heavy ion collisions, we energy of the system is much higher, like now 8, typically 8, something like this. And so this is similar to the binding energy of a nucleus. So this means that the nucleus can be broken into free nucleons in principle, but this actually doesn't happen. And even if the energy is high, still we have a lot of fragments and clusters. Okay, and even if we raise the energy by factor 10, if we go to 80 MeV per nucleon, we stay. So this corresponds to the energy around here. So still we don't have a gas of nucleons, but we have a gas of clusters in here. Okay, so I want to say that the clusters appear in really in a wide range of phenomena in nuclear physics. Okay. And then about the transport models, we need to solve the time evolution of the reaction. We have to use some model, and so such models are usually called transport models. And here this was taken from our transport model comparison project from this first paper, and there are many BUU codes and QMD type codes, and but in this comparison we have not yet studied cluster production. But some models here can describe cluster production in some way. For example, QMD models basically describe fragment production. And also in BUU models, some models like PBUU include cluster correlations. And also SMF include fluctuation in one-body density, phase space density. So this can also describe fragment formation. But for many transport models, fragments and clusters are not really easy to describe. Okay. And when we talk about fragments or clusters in transport models, I think there are several different meanings. So I want to summarize the situation here. First of all, if we can solve the time evolution from the beginning for sufficiently long time, then if we come to this situation, it's very easy to to identify fragments. Okay, you can easily identify by your eye. Here is a fragment, and then you can count the number of neutrons and protons, and you can see what was produced here. Okay, so this is simple if we can do this. But one thing is that the fragment here is usually excited, so we need to calculate the decay of such an excited nucleus. But this can be done by using another code, like statistical decay code such as Gemini and so on. Okay, so this is a simple problem, but sometimes we cannot solve the time evolution reliably for such a long time, and then in some models we have to try to get the information of clusters at a relatively early time, maybe around here. And this is typically done for BUU codes, usually called coalescence prescription, to identify the clusters around here. Also in QMD codes, Saka or Frege method try to get the information of clusters at a relatively early time. Okay, this is the second meaning of clusters or fragments. And then this top one is about the correlation at a still earlier time. And here, there may be some cluster correlation. A cluster correlation means that several nucleons may move together for a while. So such a correlation may exist in this phase. But of course, such clusters will not be necessarily emitted. But the existence of correlations may affect the time evolution. So in the following, I will introduce in the model is the correlation around here, and then of course the correlation here may also affect what will happen at the end. But we want to put clusters in the dynamical situation in the following. Okay, and such approach is not, there are not so many models to include such cluster correlation, but first, I think this is the first case that the cluster correlations were introduced into BUU model, and this was done by Danielewicz and Bach already in 30 years ago. And in this approach, this is an extension of BUU model. So they consider the phase space distribution of neutrons and protons, and this is normal. But also, in addition to neutrons and protons, they consider deuteron distribution, triton, and helium-3. And the BUU equation, usually considered for neutrons and protons, is extended to include deuteron, triton, helium-3, and also in the right-hand side there is collision terms. So by the collision terms, these different equations are coupled. Okay. And in this way, this shows the spectrum of protons and clusters, and the model was able to describe the spectrum, shape of the spectrum reasonably well. Okay, so this is a way to extend the BUU approach. And in my case, I will take another way, maybe similar physical meaning, but a different method by extending AMD, antisymmetrized molecular dynamics. So from here, I want to explain our model. And in AMD approach, we use an antisymmetrized or Slater determinant of Gaussian wave packets. So we have many wave packets. Each wave packet corresponds to a nucleon, but the total system is antisymmetrized. And the time evolution is determined by, okay, so there is a centroid variable Z, and Z is a complex variable, and the real part is the position. And in this expression, the imaginary part of Z corresponds to the momentum. And we have a width parameter nu here. Okay, and also we have a spin isospin state here. And time evolution of the wave packets is determined by this first term. This first term is derived from the time-dependent variational principle. So this is a deterministic term. This is like an equation of motion in classical dynamics, but a little bit affected by the antisymmetrization. But formally, we can write this way by using a Poisson bracket. And this here we have a Hamiltonian, and Hamiltonian is an expectation value of the effective interaction, and we need to assume some effective interaction such as a SCAM interaction. Okay, so this effective interaction can be related to the equation of state. So the information, you can think that the information of the equation of state is in here. And in addition to this term, we have a nucleon collision term. And this is similar to all QMD cores. And so two wave packets may collide and they are scattered randomly to some direction. And this may be written in this way. So this is an energy conserving transition caused by a nucleon interaction, and so this is just Fermi's golden rule, because we need to take into account the Pauli blocking for this. And the important thing is that this is a stochastic term in QMD or AMD approach. So scattering angle is a random number. Okay, so here I said that we do antisymmetrization, and because of the antisymmetrization, in many cases, the effect of antisymmetrization is not very intuitive. For example, if we have two wave packets very close to each other, and if we do antisymmetrization, the total antisymmetrized wave function, you can see that this is equal to a Slater determinant of S wave and P wave single particle wave functions. So this is a case that antisymmetrization is not very intuitive. Some people know this very well, but some people are not familiar. So I have this. So for example, the ground state of carbon-12 may be described by 3 alpha clusters, and this is almost equivalent to the shell model-like configuration like this. Okay, and this is about effective interaction. If we need to know, we use usually SCAM interaction, but we don't include the spin orbit interaction in my AMD calculation. Also, in all the calculation, I also used finite range Goni interaction. Okay. And so as I already shown that the equation of state of AMD is like this. We have a deterministic term which includes effective interaction on the information of the mean field or equation of state. And also in addition to us, we have a stochastic nucleon collision term like this. So by this stochastic term, starting with a single initial state, we can reach different final configurations randomly. So so this should be so many reaction channels will appear by solving this kind of stochastic equation. Okay, so I think stochasticity is quite important to describe Hebbian collisions. Okay, and for the collision term, we need to assume some cross-section. And about this, I will come to talk about this later a little bit more in detail. Okay, so this is still without cluster correlations, and with this very basic version of AMD, some reactions were successfully described, but usually the model didn't work very well. For example, this is a xenon-tin central collision, and as you can see, basically two nuclei penetrated each other, and you have two big fragments here and here. And if you compare with calculation with indoor data, we had too many heavy fragments, and we didn't have enough intermediate mass fragments around here. And also you can see that we had too many protons and too few alpha clusters. So if we compare the number, we had too many, 40 compared to the about 10 in indoor data, and alpha cluster is much fewer. So this shows that usual very basic version of AMD is not good at describing the expansion of the system, and there are too many nucleons are emitted at the end. Okay, so to go beyond this, there are several approaches to improve the situation, but one of the way was to include cluster correlations. Okay, and to put what I mean by cluster correlation is this way. So in usual case, two nucleons are just scattered. So this is a usual two nucleon collision. But in an improved approach, we consider we still consider two nucleon collision, but in the final state of a collision, for example, this one may form a cluster with a third nucleon, so to form a deuteron. So this is still a transition from the initial to a final state, but now final state includes this kind of clusterized configuration. Okay, so this is a difference between the usual nucleon-nucleon collision and the nucleon-nucleon collision with cluster correlation. So more generally, we can say in this way. So maybe this way, or you can see this diagram. So basically, two nucleons collide, but in the final state, each nucleon may form a cluster with something else in this way. So, and the transition probability is maybe considered like Fermi's golden rule. And then what we have is that here we have still a matrix element for this nucleon-nucleon interaction. Okay, and in addition to this matrix element, we have these overlap probability to form cluster at the end. Okay, and the matrix, so overlap probability may be calculated automatically by using some wave function, and the matrix element is taken from the nucleon-nucleon scattering cross-section. So we may use a free nucleon-nucleon cross-section, or we may use immediate nucleon-nucleon cross-section, and this determines the matrix element here. Okay, so this is maybe a little bit complicated, but still easy to understand, I hope. And by putting this correlation, the situation of the fragmentation of cluster production is now can become very good, as shown here. Now we have really some kind of multi-fragmentation. We have enough intermediate mass fragments, and we have a good number of protons and alpha clusters. This part shows a cluster yield weighted by the mass of the cluster. So alpha cluster is really important. This is an important fraction of the total system, and this can be well explained by including a cluster production. Maybe I forgot to say that I consider up to the formation of alpha cluster, 4-body cluster in this method. Okay, and here this is to intuitively understand why cluster correlation has so drastic effect from here to here. Let's consider 4 nucleons at the temperature 10 MeV. And if these four nucleons are not correlated, then the energy may be like 2/3 of the temperature times we have 4 nucleons, so energy is 60 MeV on average. But if these 4 nucleons form a cluster, then we only have one center of mass motion, and we have binding energy. So energy is minus 13 MeV, I think. Then this difference is more than 70 MeV by forming an alpha cluster. So this kind of thing can affect, I think, a lot to change from here to here. Okay, and also there are many alpha clusters, and so we need to so cluster correlation should be considered consistently with collision dynamics. And this shows the number of clusters during the time evolution. So at first, I didn't assume the existence of cluster, but by forming a cluster, we can count the number of cluster. And this shows that this vertical axis, range of the vertical axis corresponds to the total number of the nucleon in the system. And so empty region shows the number of nucleons which are not in a cluster. And so blue part shows the number of nucleons in 4-body cluster, and green is in 3-body cluster. The red part is a 2-body cluster. So you can see that most of the nucleons are in clusters already around this time. Okay, so because this should have a stronger impact to change from here to here. Okay, and this slide shows some more things about the cluster correlation. One thing is that when we make a cluster, cluster is still made of nucleon wave packets. So this is actually nothing special, but several wave packets are at the same place. Okay. So for example, this cluster may be broken by if one of the nucleons in the cluster is scattered by something else in this way. So then this cluster may be broken later. Okay, such a breakup of cluster is automatically taken into account. And also the medium cluster may change its property, but I will not talk about this here today. And also this thing, there are many possibilities to form clusters, and this may be important to think about. So I will explain this. So let's think that these 2 nucleons are now scattered, and this may form a cluster with something else. Okay. If there is one nucleon around here, then it's easy to think about how to make a cluster. But usually there are many nucleons. For protons, there may be many neutrons. Then this may form a deuteron with B1, or this may form a deuteron with B2, or this may form a deuteron with B3. And then there are many possibilities. And the big difficulty is that these final states are not orthogonal So we cannot add the probability in a simple way, but we need to construct some kind of projection operator to this subspace spanned by these final states. And then we can calculate the probability of forming a deuteron in this case. And then for this probability, we will choose one of the partners to make a cluster. And also it's possible that the cluster is not made with any neutron in this case. Okay. And this procedure is repeated not only with a nucleon, but with other particle species. And so this, maybe you can think how to do this, but then by relatively simple way, we can consider the formation up to alpha cluster. Okay, and this is something additional about the formation of a little bit heavier nuclei. So far I was talking about the formation of alpha cluster or triton cluster, but also it's possible that 2 clusters or 3 clusters may form a light nucleus like lithium. And for example, lithium is a very weakly bound state of 2 clusters, and forming this light cluster is also a difficult problem. And it seems that the formation should be directly considered. So sometimes I put this kind of light cluster formation dynamically. And for this, we need to take care about the energy and the momentum conservation with something else. So this should be a little bit complicated situation. But this shows that such a production of light nuclei seem to be very important. For example, this is a carbon-carbon at 25 MeV per nucleon, and studied by Chinese colleague and Wada-san in Texas. And it shows that to explain the light clusters like this, sometimes they are emitted at large laboratory angles. And to explain this, it seems that they should be rather directly produced. This shows the excitation energy of these light nuclei. You can see that lithium or lithium-6 may be formed already at the ground state at the end of the AMD calculation. Okay. So maybe, okay. So here I may need to talk about how to choose the matrix element in medium. And in principle, I can use a free nucleon cross-section for this matrix element, but usually people use in-medium effect. And also here, I can put some in-medium effect in the matrix element. And this explains some details about how to do. And we need to, the matrix element depends on a kind of density rho prime defined in this way. Okay, so this is about the medium matrix element, and also cluster formation. There are some discussions that in nuclear medium, the cluster may exist or may not exist, and maybe it's true that at high density cluster don't exist. Then we can turn off cluster formation at high density. And this can be a parameter for the calculation, the critical density. And later I will show an example that the critical density was taken in this, at this value. Okay, okay, so, and in addition to this, maybe about the this cluster forming probability, we need to assume some wave function of clusters, and we take this width parameter of the cluster internal wave function. And as I said, this is about this problem. there are many different cluster formation configurations. And so we have, so transition rate depends on the final configuration, and the probability is normalized in this way. So this is fine. But then final momentum shown by red color, okay, after taking care of the energy conservation, final momentum is determined, okay? And this final momentum depends on the cluster configuration. So this can be a little bit complicated situation, but this is done in this way, okay? So, and sometimes this is important because by making a cluster, we gain some energy. So this energy will go to the relative momentum between scattered particles. So this P relative can be large after the cluster formation. So then also this denominator, this corresponds to velocity, a kind of velocity, and this part can become large by forming a cluster. So this increases effect of the two nucleon collision and increases, so phase space factor increases by the cluster formation, and also by a single collision, effect of the momentum transfer increases. And so this kind of effect may be important after including the cluster formation. And such an effect of the collision term is directly reflected in stopping observables. So I will talk about the stopping a little bit here. And stopping is like this. So by a collision, the strong stopping means that the system stops completely and may expand almost isotropically. Or weak stopping is like this. Mainly particles are emitted in forward and backward directions. This situation may be quantified by this kind of quantity. This is a kinetic energy in the transverse direction, and the denominator is kinetic energy in the beam direction and in the center of mass frame of the system. And maybe you may add the energies for all charged products or for some selected particles, depending on your purpose. And this kind of observable has been studied experimentally by several collaborations. And at low energy, in really low energy, I think this corresponds like a fusion reaction, so emission is isotropic. Okay, so this stopping of observable becomes 1 if for the isotropic expansion, okay? But at Fermi energy domain, it becomes like this, and maybe because of the Pauli blocking or incident energy is high, and high incident energy cannot be stopped sufficiently. So the stopping is intermediate here. And if you go to high energy, stopping can raise, can go up this way. And but you may be careful because green line is xenontin and red line is go. I couldn't find a good data in publication for go on xenontin for all energy range. But this may be connected, but at high energy, xenontin system may be weaker stopping, and this is actually shown in this way. And this is a function of the stopping, but this is a stopping observable, but as a function of the final the particle. So this is calculated from hydrogen, helium, lithium. So this quantity depends on the final particle, and you can see that go and xenontin, depending on the mass of the system, this stopping become weaker for lighter system. Okay, and now I can compare this xenon tin or xenon CSI system with AMD calculation. So as I said, that we may have an option to use in-medium nucleon matrix element, or we can change the option to use a free nucleon matrix element, or we can change whether the cluster is produced only low densities or clusters are produced all the time. Okay, so by changing these options, stopping observables change in this way. So this blue band corresponds to this green FOPI experimental data for xenon CSI, and calculation result. So stopping is weak here compared to this situation. Okay, because you can understand this change by this change of the input parameter, but the charge distribution of fragments or particle ease didn't depend much on this kind of input parameters. But if we really turn off cluster production, so this is a very basic version of AMD, then we don't have clusters at all, and we have too many neutrons, protons, maybe too many protons. Okay, so this doesn't work at all. And this shows a PZ over A, or rapidity. You can think that this is a rapidity distribution for alpha for these particles. And you can see that this distribution is of course related to the stopping, and depends on these parameters in this way. Maybe the real situation may be between this and this. Okay, and okay, and this shows okay, this is for the information on the beam axis, and this is mainly the information on the transverse direction. This is the energy of particle divided by the mass. So this corresponds to the velocity or energy per nucleon. And you can see that the high velocity part is mainly neutrons and protons, and low energy part or low velocity part, you can have a large fraction of clusters. Okay. Now I want to talk about this symmetry effect. This I already discussed at the beginning of my talk. People want to see this effect. And one is pion observable. And we actually did some work on the pion production. And we see that some effect here can be reflected in the final pion ratio. But I'm not going to talk about this today. But I want to talk about the nucleon or cluster observables. And this effect can be also shown, same effect is shown here. Now this is the situation at T20. So this time, high density phase. And this shows the difference of the neutron density and proton density. So as shown here, the central part is less neutron rich than the average. And this difference is depending on the symmetry energy, stiff or soft. And of course, total number of neutrons and protons are conserved. So this central region, effect of the central region is compensated by the effect in the exterior region. Okay. And then the question is whether this can be seen in the final observable. And if the time progresses, the system is expanding in this way. So everything is expanding. So but as you can see that the effect here remains during the expansion. The difference between two symmetry energy still exists at the late time. This originates from the early time effect, okay? And this black line shows the radial velocity as a function of the direction from the center. So the exterior region is expanding rapidly and the interior region is slow, right? And then this means that the effect may be observed in the final energy spectrum. And actually, the effect at early time seems to be mapped in the energy spectrum here. And this shows that this quantity, I added all neutrons in these clusters and also free neutrons. And in the denominator, I added all protons in clusters. And then this is a function of the energy per nucleon, and the ratio was taken. And then this is, so the final observable here is very similar to this. So this means that this low velocity part was originally high density part in the system. And so this effect comes to here, okay. So if this can be seen in experimental data, I hope we can talk about the symmetry energy at high density. And in fact, the spirit data were the experiment was performed at the RIKEN RIBF factory several years ago. And Kaneko-san analyzed the rapidity distribution from this experiment. The experiment was done for various combinations of thin isotopes, such as this relatively neutron-rich system and also this less neutron-deficient system. And here, experimental data from SPIRIT are shown by black points, and lines show AMD calculation. And the AMD calculation were done with different choices of nucleon cross sections. And in a choice, we see, for example, here, we have a little bit transparent, weak stopping. And if we increase the nucleon cross section, the rapidity distribution changes like this. And with some choice, experimental data may be fitted this way. And also, we have neutron deficient system and neutron rich system. And of course, yield of clusters depend on the neutron richness. And in particular, you can see that the tritons are very, tritons changes a lot from neutron deficient system to neutron rich system. Of course, tritons include 2 neutrons, so it is carries strong information on neutron richness of the system. And then, then we hope that this may have some information of the neutron richness of the central part of the system. So here we show the ratio of triton-proton, and also we took the double ratio of neutron-rich system and proton-rich system. And maybe if I take double ratio, it's not very easy to explain, but maybe we can focus on this neutron-rich system. And in neutron-rich system, as I said, that the central region has a symmetry energy effect, and tritons are mainly formed in low velocity part. So Triton's, I hope, has information around here. And in fact, for this double ratio, we also see the dependence on the symmetry energy. So for soft symmetry energy, we have a larger value compared to the stiff symmetry energy case. And it seems that experimental data shows that this central region, this effect of the symmetry energy is not very strong. So this is more consistent with calculation with soft symmetry energy compared to the stiff symmetry energy. Okay, and so this was the main conclusion from this paper. But of course, we need to here we only see the for tritons or hydrogen isotopes, but also the study should be extended. And also we are now working hard to study the triton helium-3, and also stopping need to be understood consistently. And also other observables such as corrective flow are now studied, and the study is now in progress. And I hope we can show you more complete picture of the reaction in near future. Okay, now I want to summarize my talk. And as I said, we need to consider cluster production in heavier collisions, in intermediate energy heavier collisions, because anyway, clusters are fragments as the main products, and we cannot ignore them. Also in experiment, these clusters are used to extract important physical information such as the equation state. And the description of clusters is a long-standing theoretical challenge, and it's really a quantum mechanical process. And such a quantum correlation has to be considered in highly excited system. And AMD incorporates such cluster correlations in the final state of every two nucleon collision. And my main purpose was to talk about clusters in expanding the system. And in expanding system, the low velocity part, mainly from the low velocity part, clusters are formed. And then this part originate, so this part is a central part of the expanding system, and it originates from the high density part of the expanding system. So equation state information may be seen, I hope, in the cluster observables. Okay, but we still need to work on some remaining problems. Okay, thank you very much for your attention.
Okay, so thank you very much, Ono-san. So yeah, I'm Gojo. Nice to see you. Nice to see you.
So
yeah. So Professor Ma is just away for a while for some duty. So let me host the next question sections. So
okay,
yes, first, thanks for this nice talk. And I think Ono-san gave a very detailed discussion about the class formation in the collision using AMD. So if you have any questions, please hand up. Okay, thank you.
Hello, Zhubo.
Okay, please.
This is Yan Ye from Peking.
Yeah, Professor Ye, please.
Very nice to hear Ono-san's voice for quite a long time not seen. I'm just a little bit curious about the definition of clusters during the evolution of the collision. When we talk about clusters in free space, of course, the stability depends on the bounding energy or bounding situation. During the collision in the environment of the nuclear matter, do you have an idea of how stable is this kind of cluster? Could you estimate the stability or bounding energy relative to the environment or something?
Sorry, today I don't have any slide about this, but then in the MD calculation, we put the cluster here. And this cluster is interacting with other particles, but I mean by the interaction or mean field interaction. So the binding energy of such a cluster in such an environment is not same as free binding energy, and I think this is partly automatically included in the calculation, but we cannot adjust this because this already we put some interaction such as a SCAM interaction, and by assuming the SCAM interaction, everything is determined by this interaction. I remember that if I calculate the binding energy of alpha cluster in a nucleus by assuming a SCAM interaction, I saw that the binding energy of alpha cluster decreases in the nucleus.
Yes.
Yeah. Unfortunately, I cannot adjust this. It's already in the model. So does this answer to your question?
Yes. It depends very much on the density around.
I think so.
People estimated that when you go into high density, the banding almost reduced to zero.
Yes,
and when you go to the low density, even to the free space, it increases the banding.
But also binding energy depends on the momentum of the particle or temperature of the surrounding medium. So actually, usually a calculation is done for assuming sometimes usually at zero temperature, but the final temperature calculation can be done.
Also, your interaction. As far as I know, when people talk about the structure case for the cluster formation, usually they need to use the so-called density-dependent interaction. Otherwise, it's difficult to get the spiral formation. How about your interaction? It's also density-dependent?
SCAM is always density-dependent. I use this kind of SCAM interaction, and so this term is a density-dependent two-body interaction. This is always important. Also to be consistent with saturation of nuclear matter, this term. Anyway, this term was introduced to explain the saturation of nuclear matter. So to explain various nuclei from light one and heavy nuclei, this is usually important. I think.
Okay, thank you.
Thank you very much for your question, the discussion.
Okay, thank you. So Shenlei, please.
Hello, Ono-san.
Hello.
I'm Shenlei. Thank you very much for your report, and I have a few questions. At the very beginning, you say that your study shows the influence of the cluster correlation on the final state. It means that there is no cluster correlation in the initial state. Is that?
For example, this one. initial means that the initial state of a collision or initial state of nucleon scattering. There are two meanings.
The initial state of the collision process.
Yeah, heavy
Is
ion
there
collision.
a cluster? You say that you want to study the cluster correlation at about 50 Fermi, like in the middle picture here.
Yeah.
Is that?
Yeah. Yes. Actually, this quantity does not have absolute physical meaning. I'll say that this depends how I count the number, but then so the initial value is rather arbitrary. I mean, we always have a Slater determinant of nucleon wave packets, right? So whether we say that there are clusters already in a projectile nucleus and target nucleus, or they are independent nucleons, this is just the difference of what I say, and it's not a difference of the physical state. So in this case, this part you don't need to think this part has some physical meaning, but what you can see here is that there are many this kind of production of cluster and destruction, and around here these particles are nucleons are produced in this way. So after this kind of process, this is counted as a cluster. And I hope this does this answer your question?
Okay. And I have another question is that the cluster correlation is added in the two nucleon collision. Is that? So yes. How does it create a larger cluster? So do you treat the cluster as a whole particle?
Cluster is still made of nucleons, and I put several wave packets at the same place. So this is what I call cluster. Okay. And so your question was how this equation is evaluated, or how this cluster is actually constructed in the calculation. Maybe
I mean that like how the triton or alpha cluster is created, because you only add the cluster correlation in two nucleon collision.
So I mean, okay, you what you say is that then here N1 and B1 is coalesced and C1 is made. So this should be a two-body cluster, right? Is this what you want to say?
Yeah, okay. It's a two-body cluster. Yeah.
Okay, so this is a two-body cluster. And okay, so this should be extended in some way. Or actually B1 is not nucleon, may not be a nucleon, but then it's a set of several nucleons. Actually.
Oh, okay, I see.
I'm sorry. So I said that this is something else, but I didn't say this is a nucleon. but technically, to find many particles to form an alpha cluster is technically difficult. So actually, this is done this way. I first consider okay, so let's say, so this is a proton spin up. then I will first consider a formation of not with proton spin up, but maybe proton down or neutron spin up or neutron spin down. This is randomly decided. Then, so in this case, I consider a formation of a cluster with a neutron spin up, and then maybe a cluster is formed here, but then I still continue the formation with maybe neutron spin down. And then this is a deuteron, but by forming a cluster further with neutron spin down, you can create a triton. And then at the end, if I consider formation with proton spin down, then alpha cluster may be formed. So by considering this loop in the code, I get the cluster is formed by this iteration in the code.
Okay.
So this was relatively easy to do, but only up to alpha cluster. I don't know how to do for heavier nuclei, like Rickenn.
And after the cluster created, does the Hamiltonian in the equation of motion change?
I didn't change anything. So this is still, I call it cluster, but it is still made of nucleons. So just two wave packets or three wave packets are at the same place. And so this is still a AMD wave function. So we don't need to change the equation or equation motion or Hamiltonian.
So does the position of each nucleons in a cluster are exactly the same?
Yeah, wave packets
are the same.
Yeah,
oh, okay.
So because it's a wave packet, so it has some distribution, Gaussian distribution, but they are overlapping at the same place in phase space, same position and the same momentum.
Okay,
so
thank you very much.
Usually they will move together for a while, but if one of them are scattered in this way, then the cluster may be broken. So this part is very simple. I didn't do anything special.
Okay, thank you very much.
Okay, so next, Professor Guoqiang Zhang. Sorry, you should turn on. Yes. Okay. Okay.
Hey, thank you. Thank you, Professor Ona. A very nice talk. I'm shocked to see without any statistical decay code, you can fit the cluster distribution of fragmentation so well with the experiment. So I'm wondering, actually, I have two questions, but one of the questions already answered by you just now, Nathan. So you don't change the framework of AMD. You treat every nucleon the wave packet, so it's under the framework of AMD totally. So you add some parallel progress to see whether there's a cluster or not. Is it? Am I correct? So you don't change the code AMD wave function, but you just see every time step whether they form the cluster or not, but you don't you don't interfere the nucleon or wave packet evolution. Am I right? Okay.
Yeah.
Okay. Oh,
yeah,
so
all nucleons are treated.
So it's still under the framework of the AMD.
Yes.
Okay. Yeah.
Yes.
Thank you. Another question is when I see about the collision. So can you treat the collision with the mean field in a unified way. So why we need to treat separate? Why we need to separate the collision part and the mean field parts into two? Actually, when I discuss with people from material science or condensed physics, they say, why you treat another collision? They can treat in a mean field unified way. So if you use a hardcore potential, maybe they can crack each other in a uniform way. But you are using
usually,
yeah.
This doesn't have a hardcore, right? This is this part is a very smooth mean field potential.
So you mean
so because this collision term may be simulated by adding some hardcore two-body potential. But this may be technically possible to do, and but physically or as in the nuclear problem, I think, for example, this kind of nucleon scattering is usually described by quantum mechanically, right?
Yes.
We don't solve classical Newton equation to simulate nucleon scattering. So this kind of stochastic way rather correspond to this standard quantum mechanical scattering treatment. So in this sense, I think stochastic way is more, how to say, faithful to quantum mechanics. Yeah.
Okay, maybe the mean field would be too soft. So that's why we need some collision process to. Actually, when people doing electron, they don't need to add this kind of collision process.
I think for I don't know the collision between electrons, but the collision between ions can be treated usually classically, I think.
Mean field,
yeah. I think usually molecular dynamics is used for the motion of ions.
Ions,
ions, nuclei.
But
they are much heavier than electrons. So the time evolution can be well approximated by classical motion.
Okay.
In that case, it's natural to treat everything by classical motion with some potential. Nuclear case is
okay. Do you think is it possible to add some hardcore potential to simulate the collision between nucleons?
I don't know. But of course, there are. Sorry. Some people use classical molecular dynamics to I'm not sure if I can say that they simulate heavy ion reaction, but they study something related to heavy ion reaction. Some kind of a general feature of phase transition kind of thing. Still, classical molecular dynamics is used. But really to calculate the time evolution of the heavy ion collision, I don't know if the method was successful or not.
Okay. Okay. Thank you.
Maybe I forgot something.
Okay. Thank you.
Yeah, you are welcome. Thank you very much for your question.
Yeah, okay. Professor Chang, please.
Thank you, Professor Ono. I had several questions. Thanks for your excellent talk. My first question, could you hear me? Can you hear me?
Yeah. Yes, I can. Sometimes it's difficult to find who is talking. But I see.
I'm not sure. My microphone is working.
Working.
Okay. Please turn to page 20.
Page 20.
Yeah. Let's see. You mentioned cluster formation may be turned off depending on phase space density.
Yeah. Yes.
When the nucleon density in phase space is too dense, then cluster formation is turned off. And for example, in the spectator regions, cluster formation is turned off. But you mentioned in another page, cluster formation is turned off when the nucleon density is above 0.125. So 0.125 is not a very low density. It's not a very low density. So here. It's not a very low density. And so even spectator zone, for spectator zone, in the spectator zones, cluster formation may still be possible. And this, I think, would utterly distort the dynamics. And I'm not sure, have I got it right?
I don't know at which density is most suitable. So this is just a example of parameter. But
so for example,
please continue.
Please. Oh, okay. So for example, even a not very excited patch of nuclear matter may automatically fragment into pieces because of cluster formation, because of this not very low density cut.
You are worrying that some nucleus may unphysically break up into pieces. Of course, heated nucleus may physically break up into pieces, but then if it's not sufficiently heated or density is high, it will not break up. And actually, even if clusters are formed in a nucleus, they are still interacting and they may still bound in the nucleus. So forming a cluster does not necessarily mean that they will appear and break up. Because forming a cluster makes the system to break up. It makes it easy for the system to break up, but then this does not necessarily mean that the system will really break up. Do you understand? It facilitates the breakup, but still clusters may.
Yeah, because it produces a fluctuation of density in the region. I have another question. Page 25.
This page?
Oh, yes, yes, here.
There are 225.
25. In the talk, you mentioned the conservation of energy. Is it treated after cluster formation or before cluster formation? Because here the relative momentum appears in the numerator, and the relative momentum is a key information in the calculation, in the evaluation of the overlap matrix. So, if you change this relative momentum after for adjusting the total energy, then the matrix elements will change. Is it right?
Yeah, you're very right. Yeah, so this final energy is final energy after cluster formation. So this P relative depends how clusters are formed.
Yes.
So as you said that the overlap probability here, this anyway depends on the how the nucleons are scattered, and this depends on the energy conservation. So also matrix element may slightly depend on this final momentum.
Yes.
So you are completely right. So, and this was taken care of in this formula.
But before, okay, please. Yes.
Yeah. So
continue.
So this is calculated as you said exactly. So,
but before the selection of clusters, which one is selected, all probabilities. Before the selection of clusters, this relative momentum is a key information in calculating the overlap matrix. How do you know the relative momentum before you select, before the selection of clusters?
Okay. So this is I need some numerical technique about this, and the method is I will put some guess of this, okay, and then we decide we choose one of the possible configurations following this guess value of the probabilities. And then after choosing a configuration, I can calculate the energy conservation and I can know the correct value of the P relative. And this P relative is different from the first guess of my calculation, right?
But the selection, I mean, the selection is not changed. The final result, which probability is selected, is not changed.
But it is changed later. After I know this true value of P relative, the probability will change. Right? And this change was considered by, I would say the previous guessed value is replaced by this true value. Or if I'm doing some random Monte Carlo method or something like this, then I am here with some guessed probability, but this probability was wrong slightly. Then I have to modify something to correct the probability to the right one. Sometimes I will cancel the collision, or I have to enhance the probability of the process.
Okay, it's still beyond my understanding.
Yeah.
Thanks for your kind explanation.
This needs some trick, and
yes,
at the end I need to do some modification of the probability.
Okay, because
writing the formula is very easy, but to do the calculation is complicated.
Because different results has different results have different probabilities and different relative momenta. So it is difficult. Okay.
Maybe because this is some assumption, and you may find a better way to
okay, thanks. That's all my
thank
questions.
You very much for, thank you very much for your question. Very good.
So, okay, so please, Professor Hua, please.
This is Hua from Shanxi Normal University. Thanks for your nice talk. I have a very simple question. When the cluster is formed in AMD with the cluster correlation, are the clusters in the ground state, or they can have the possibility at the excited states?
In my calculation, I only consider the ground state of the cluster. And maybe it may be interesting to include the excited states of alpha cluster or helium 4, but this was not considered in this calculation.
Okay, thank you.
Thank you.
So, okay, any questions? Ono-san, so sorry, I want to ask 2 questions. One is about the time evolution in AMD. So sometimes the nucleons probably will go away, right? Because they should sometimes, I mean, if they are little far, then there are no interaction, then the nucleon will kind of disappear. So how to deal with these kind of things in your model?
It should be automatic. I mean, maybe like this one. For example, nucleon may go out.
Yes.
Yeah. Then this basically this I don't need to do anything special, but this will not interact with anything else, and this will not collide with anything else. So this will just flying. So basically, I don't need to do anything special for this non-interacting particle. But also, computationally, it's good to separate this one from the other systems, then computation can become faster. And this is actually done, but conceptually, you don't need to worry about this one.
Yeah. Okay. Another limit is if two nucleons are too close, do you have treated or it automatically? You don't need to think about this. I mean,
too close.
Yes.
Do you worry about the singularity?
Yeah. Right. So.
So you worry that when two-wave packets are placed at the same point, then the norm will become zero. Is this what you?
Right. Because somehow it will lead to some numerical problem.
Yeah. So sometimes, sometimes this may happen, and maybe once in 100 events, computation stops for some reason. I don't know why this happens, but usually we don't fall into singularity. For example, okay, so after two nucleon collision, I change the momentum of a wave packet, and then if the final nucleon comes at the same point with something, the other nucleon, then it becomes singular.
Okay.
In such a case, I check the distance between other wave packets, and if really dangerous, I will skip this collision. But
okay, okay, yes.
But this is a really rare case.
Okay, yes. So another thing, yes, you said you introduced the alpha correlations, and if a little heavier fragment, for example, lithium 7s, in that part you said very difficult. So I want to just confirm the difficult part is there are many channels, many possibilities to form that lithium 7. But if you do it, you just introduced, it's very difficult, right? Because you don't know it is just alpha triton or helium 5 neutron. You cannot. We don't know the cross section. So in that sense, it's difficult to introduce that correlation, right? Or what do you the most difficult part? What do you mean the most difficult part to introduce that heavier fragment correlation?
Maybe in this slide I showed a very simple assumption. So this is not difficult, but then to form lithium in this way is maybe so the method is simple because up to alpha clusters I can make a cluster by S wave packets, right? Up to alpha cluster, but to form lithium, I need to worry about how to make the clusterized state.
Yes,
and to consider this for not only lithium 7 but for all other clusters, I think it's not so easy. So for lithium, beryllium, for the moment, I need to do some.
So if you can introduce in some way, in some simple way, so what do you expect after that? If once you introduce, so the final result will change something or not so much difference?
Yeah, So I think they affect a lot. I mean, if I don't introduce lithium, barium, then usually the system tend to become a gas of clusters, gas of light clusters. So I will have too many alpha deuterium tritons, but I don't have enough. Maybe to have, maybe I will have a lot of light particles, alpha particles, and light clusters. But this part, this part cannot be described. It's not like this, but maybe drops down sharply. So basically, I will only have alpha cluster and light particles at the end. There is such a tendency. So when I include light clusters, then I have to introduce something to bind clusters to form heavier fragments.
Okay, thank you very much.
So
yeah, so any questions? Yeah. Okay, so I think that's all. So finally, thank you very much, Ono-san. So thanks.
Thank you very much.
Thank you again. Yes.
Thank you very much for your questions and very nice discussions.
Thank you.
Okay,
thank
so maybe today we can finish. So thank you for your participants. So,
okay,
yeah.
bye-bye. Give my best regards to Masan.
Okay, thank you.
Okay, bye.
Okay, bye.